It is indeed possible to distribute power from a 10 MVA 13,200 volts to 13,800 volts transformer to a 25 MVA 13,800 volts to 6,500 volts transformer. However, two critical conditions must be met. Firstly, the 10 MVA transformer must be capable of handling the inrush current of the 25 MVA transformer. Secondly, the distribution line must possess sufficient capacity to handle the increased load. The inrush current of the 25 MVA transformer can indeed cause significant voltage drops along the line. The magnitude of this voltage drop is dependent on both the impedance of the line and the duration of the inrush current. While there are no specific codes explicitly prohibiting the connection of transformers of different sizes, several codes address voltage drop issues on distribution lines. National Electrical Code Article 220.10 mandates that the voltage at the point of utilization should not drop below 85% of the nominal voltage. IEEE Standard 519-2014 offers recommendations suggesting that voltage drops on distribution lines should ideally not exceed 3% under normal operating conditions and 10% during the starting of large motors. The 63% voltage drop indicated by the SKM Power Tools model is excessive. It is improbable that a distribution line would be designed to tolerate such a substantial voltage drop. The model may not accurately reflect the impedance of the line or the duration of the inrush current. To mitigate the effects of inrush current, consider these measures. Firstly, install a soft start device on the 25 MVA transformer to reduce the inrush current. Secondly, increase the impedance of the distribution line by adding inductance or resistance. Thirdly, reduce the length of the distribution line. Let's delve deeper into each of these points. Firstly, the soft start device. A soft starter, also known as a reduced voltage starter, is an electronic device used with alternating current motors to temporarily reduce the torque and current surge during motor startup. This reduces mechanical stress on the motor and shaft, as well as electromechanical stresses on the attached power cables and electrical distribution network, extending the lifespan of the system. Soft starters use solid-state devices to control the applied voltage to the motor during startup. They typically employ silicon-controlled rectifiers or thyristors to gradually increase the voltage applied to the motor. This gradual increase in voltage reduces the inrush current and torque, providing a smoother start. Several types of soft starters exist, each with its own characteristics. These include solid-state soft starters, auto-transformer starters, and part-winding starters. Solid-state soft starters are the most common type, offering precise control over voltage and current. Auto-transformer starters use a transformer to reduce the voltage applied to the motor during startup. Part-winding starters connect only a portion of the motor winding during startup, reducing the inrush current. When selecting a soft starter, several factors must be considered. These include the motor horsepower, voltage, current, and the type of load. The soft starter must be properly sized to handle the motor's requirements. Additionally, the soft starter should be compatible with the motor's starting characteristics. Soft starters offer several advantages over traditional starting methods. These include reduced inrush current, smoother acceleration, and reduced mechanical stress. Soft starters also offer protection features such as overload protection, overvoltage protection, and undervoltage protection. However, soft starters also have some limitations. They are generally more expensive than traditional starting methods. They also generate heat, requiring adequate ventilation. Furthermore, they may not be suitable for all types of loads. Secondly, increasing the impedance of the distribution line. Increasing the impedance of a distribution line involves adding either inductance or resistance to the line. This can be achieved through various methods. One method is to add series reactors, which are inductors connected in series with the line. Series reactors increase the inductive reactance of the line, limiting the current flow. Another method is to add series resistors, which are resistors connected in series with the line. Series resistors increase the resistance of the line, also limiting the current flow. The choice between adding inductance or resistance depends on the specific application and the desired effect. Adding inductance primarily limits the magnitude of the current, while adding resistance primarily dissipates energy. When adding impedance to a distribution line, it is important to consider the impact on voltage regulation. Increasing the impedance of the line will increase the voltage drop along the line. This voltage drop must be carefully managed to ensure that the voltage at the point of utilization remains within acceptable limits. Several factors must be considered when selecting the appropriate impedance for a distribution line. These include the line length, the conductor size, the load characteristics, and the desired voltage regulation. The impedance must be carefully chosen to balance the need to limit current flow with the need to maintain adequate voltage regulation. Increasing the impedance of a distribution line can offer several benefits. These include reduced fault current, improved voltage stability, and reduced harmonic distortion. However, increasing the impedance of the line also has some limitations. It can increase the voltage drop along the line, reduce the power transfer capability of the line, and increase the losses in the line. Thirdly, reducing the length of the distribution line. Reducing the length of the distribution line is often the most straightforward approach to mitigating voltage drop. The voltage drop along a conductor is directly proportional to its length. Shorter lines inherently experience less voltage drop compared to longer lines, given all other factors remain constant. This relationship is fundamental to understanding how line length impacts voltage performance. When evaluating the feasibility of shortening a distribution line, consider several practical aspects. Firstly, the physical constraints of the site might limit the relocation of transformers or other equipment. Secondly, the cost of relocating equipment and rerouting conductors can be substantial, requiring a thorough cost-benefit analysis. Thirdly, the impact on the overall system layout and future expansion plans must be carefully assessed. Reducing the line length offers several tangible benefits. Primarily, it reduces voltage drop, ensuring that the voltage at the load remains within acceptable limits. Secondly, it improves voltage regulation, maintaining a more stable voltage supply under varying load conditions. Thirdly, it reduces line losses, improving the overall efficiency of the power distribution system. However, reducing the line length also has some potential drawbacks. Firstly, it may require significant capital investment for relocation and rerouting. Secondly, it may disrupt existing operations during the construction phase. Thirdly, it may limit future flexibility in terms of load expansion or system reconfiguration. Now let's discuss inrush current in more detail. Transformer inrush current is a phenomenon that occurs when a transformer is first energized. It is characterized by a large surge of current that flows into the transformer windings for a brief period. This inrush current can be significantly higher than the transformer's normal operating current, often reaching 10 to 15 times the rated current. The magnitude and duration of the inrush current depend on several factors, including the transformer size, design, and the point in the voltage waveform at which the transformer is energized. The inrush current is caused by the sudden establishment of magnetic flux in the transformer core. When the transformer is first energized, the core is unmagnetized. As the voltage is applied, a large magnetizing current flows into the windings to establish the required magnetic flux. This magnetizing current is limited only by the impedance of the windings, which is relatively low. As a result, the inrush current can be very high. The inrush current typically lasts for only a few cycles of the alternating current waveform. As the magnetic flux in the core reaches its steady-state value, the magnetizing current decreases, and the inrush current subsides. The inrush current can have several adverse effects on the power system. Firstly, it can cause voltage dips, which can disrupt the operation of sensitive equipment. Secondly, it can cause transformer overheating, which can reduce the transformer's lifespan. Thirdly, it can cause nuisance tripping of circuit breakers, which can interrupt power supply. Let's consider modeling using SKM power tools and how that ties into the situation. SKM Power Tools is a suite of electrical engineering software used for power system analysis, design, and optimization. It is widely used by electrical engineers to model and simulate power systems, including transformers, distribution lines, and protective devices. SKM Power Tools offers a range of modules for performing various types of analysis, including load flow analysis, short-circuit analysis, protective device coordination, and transient stability analysis. These modules allow engineers to evaluate the performance of power systems under different operating conditions and to identify potential problems. When modeling a transformer in SKM Power Tools, several parameters must be specified. These include the transformer's MVA rating, voltage rating, impedance, and tap settings. The accuracy of the model depends on the accuracy of these parameters. SKM Power Tools can be used to simulate the inrush current of a transformer. This is typically done by applying a step voltage to the transformer model and observing the resulting current waveform. The simulation results can be used to estimate the magnitude and duration of the inrush current and to evaluate its impact on the power system. SKM Power Tools can also be used to evaluate the effectiveness of mitigation measures for inrush current, such as soft starters and series reactors. By simulating the power system with and without these mitigation measures, engineers can determine the optimal solution for reducing the impact of inrush current. SKM Power Tools is a powerful tool for analyzing and designing power systems with transformers. It can help engineers to understand the behavior of transformers under different operating conditions and to identify and mitigate potential problems. However, it is important to note that the accuracy of the simulation results depends on the accuracy of the model and the input data. Therefore, it is essential to use accurate data and to validate the model against field measurements. Let's explore the impact of harmonics on transformers and how to mitigate those effects. Harmonics are sinusoidal voltages or currents having frequencies that are integer multiples of the fundamental frequency of the power system, typically 50 Hz or 60 Hz. These harmonic frequencies can cause a variety of problems in electrical equipment, including transformers. Transformers are designed to operate at the fundamental frequency, and the presence of harmonics can lead to increased losses, overheating, and reduced lifespan. Harmonic currents flowing through the transformer windings create additional losses due to increased skin effect and eddy current losses. These losses generate heat, which can degrade the insulation and reduce the transformer's capacity. Harmonic voltages can cause core saturation, leading to increased exciting current and further losses. The increased heating can also damage the transformer's core unwindings. Harmonics can also cause resonance in the power system, which can amplify the harmonic voltages and currents. This resonance can lead to equipment failure and system instability. Several measures can be taken to mitigate the effects of harmonics on transformers. One common method is to use harmonic filters. Harmonic filters are designed to block or reduce the flow of harmonic currents. They typically consist of capacitors and inductors tuned to specific harmonic frequencies. Another method is to use harmonic mitigating transformers. These transformers are designed to reduce the harmonic content of the output voltage. They typically employ special winding configurations or core materials to achieve this reduction. Another approach is to reduce the harmonic content of the load. This can be achieved by using harmonic filters at the load or by using equipment that generates fewer harmonics. When selecting a transformer for use in a harmonic-rich environment, it is important to consider the transformer's K-factor rating. The K-factor is a measure of the transformer's ability to withstand harmonic currents. A high K-factor rating indicates that the transformer is better able to withstand harmonic currents. It is also important to consider the transformer's Derting factor. The Derting factor is a reduction in the transformer's MVA rating that is required when operating in a harmonic-rich environment. The Derting factor is typically specified by the transformer manufacturer. Harmonics can have a significant impact on the performance and lifespan of transformers. By taking appropriate mitigation measures, it is possible to reduce the effects of harmonics and ensure a reliable transformer operation. We need to understand the tap-changing operations on transformers. Tap-changing transformers are transformers that have the ability to adjust their turns ratio, allowing for voltage regulation and optimization of power flow. These transformers are equipped with taps on one or more of their windings, which can be connected to different points along the winding to change the voltage ratio. Tap-changing transformers are commonly used in power distribution systems to maintain voltage levels within acceptable limits, compensate for voltage drops, and optimize power flow. They are also used in industrial applications to provide adjustable voltage for various loads. There are two main types of tap-changing transformers: on-load tap changers and off-load tap changers. On-load tap changers, also known as under-load tap changers, can adjust the tap position while the transformer is energized and loaded. This allows for continuous voltage regulation without interrupting the power supply. Off-load tap changers, also known as de-energized tap changers, can only adjust the tap position when the transformer is de-energized. This type of tap changer is typically used for infrequent voltage adjustments. On-load tap changers are more complex and expensive than off-load tap changers, but they offer the advantage of continuous voltage regulation. They are commonly used in applications where voltage fluctuations are frequent or where precise voltage control is required. Off-load tap changers are simpler and less expensive, but they require the power supply to be interrupted during tap changes. They are typically used in applications where voltage adjustments are infrequent or where the cost of an on-load tap changer cannot be justified. When selecting a tap-changing transformer, several factors must be considered. These include the voltage regulation range, the tap step size, the tap changer type, and the operating conditions. The voltage regulation range is the range of voltage adjustment that the tap changer can provide. The tap step size is the amount of voltage change that occurs with each tap change. The tap changer type is either on-load or off-load. The operating conditions include the voltage, current, and frequency of the power system. Tap-changing transformers are an important tool for voltage regulation and power flow optimization. By carefully selecting and operating these transformers, it is possible to maintain voltage levels within acceptable limits and ensure reliable power supply. Let's discuss transformer protection. Transformer protection is essential to ensure the reliable and safe operation of transformers. Transformers are vital components of power systems, and their failure can result in significant economic losses and disruptions to power supply. Transformer protection systems are designed to detect abnormal conditions within the transformer and to initiate appropriate actions to isolate the transformer from the power system, preventing further damage and minimizing the impact on the system. Several types of faults can occur in transformers, including short circuits, overloads, overvoltages, and insulation failures. Each type of fault requires different protection strategies. Short-circuit faults are characterized by a sudden and large increase in current. These faults can be caused by insulation breakdown, winding failures, or external events. Short-circuit protection is typically provided by overcurrent relays, which detect the excessive current and trip the circuit breaker to isolate the transformer. Overload faults occur when the transformer is loaded beyond its rated capacity. This can lead to overheating and insulation damage. Overload protection is typically provided by thermal relays, which monitor the transformer's temperature and trip the circuit breaker when the temperature exceeds a safe limit. Overvoltage faults occur when the voltage applied to the transformer exceeds its rated voltage. This can damage the insulation and lead to insulation breakdown. Overvoltage protection is typically provided by surge arresters, which divert the excess voltage to ground. Insulation failures occur when the insulation within the transformer deteriorates or breaks down. This can lead to short circuits or other faults. Insulation failure protection is typically provided by differential relays, which compare the currents entering and leaving the transformer. A difference in these currents indicates an internal fault. Several types of protective devices are used in transformer protection systems, including overcurrent relays, thermal relays, differential relays, surge arresters, and circuit breakers. The selection and coordination of these devices are critical to ensure effective protection. Overcurrent relays are used to detect short-circuit faults. They are typically set to trip when the current exceeds a predetermined value. Thermal relays are used to detect overload faults. They are typically set to trip when the temperature exceeds a safe limit. Differential relays are used to detect internal faults. They compare the currents entering and leaving the transformer. Surge arresters are used to protect against overvoltage faults. They divert the excess voltage to ground. Circuit breakers are used to isolate the transformer from the power system in the event of a fault. Let's talk about impedance. Impedance is a measure of the opposition to the flow of alternating current in an electrical circuit. It is analogous to resistance in a direct current circuit, but it also takes into account the effects of inductance and capacitance. Impedance is a complex quantity with both a magnitude and a phase angle. The magnitude of the impedance is measured in ohms and represents the total opposition to current flow. The phase angle represents the phase difference between the voltage and the current. Impedance is an important parameter in electrical circuit analysis and design. It is used to calculate the current flow in a circuit, the voltage drop across a component, and the power dissipated in a circuit. Impedance is also used in the design of filters, impedance matching networks, and other electrical circuits. The impedance of a circuit element depends on its physical properties and the frequency of the alternating current. For example, the impedance of a resistor is equal to its resistance and is independent of frequency. The impedance of an inductor is proportional to its inductance and the frequency. The impedance of a capacitor is inversely proportional to its capacitance and the frequency. The total impedance of a circuit is the combination of the impedances of all the circuit elements. The total impedance can be calculated using series and parallel impedance formulas. In a series circuit, the total impedance is the sum of the individual impedances. In a parallel circuit, the reciprocal of the total impedance is the sum of the reciprocals of the individual impedances. Impedance matching is the process of designing a circuit to have a specific impedance. This is often done to maximize power transfer or to minimize reflections. Impedance matching networks are used to match the impedance of a source to the impedance of a load. These networks typically consist of inductors and capacitors. Impedance is a fundamental concept in electrical engineering. It is essential for understanding and designing electrical circuits and systems. Let's talk more about voltage drop. Voltage drop is the decrease in voltage that occurs along an electrical circuit or conductor. It is caused by the impedance of the circuit or conductor, which opposes the flow of current. Voltage drop is an important consideration in electrical system design because it can affect the performance of equipment and the efficiency of the system. Excessive voltage drop can cause equipment to malfunction, reduce the brightness of lights, and increase energy consumption. Voltage drop is calculated using Ohm's law, which states that the voltage drop is equal to the current multiplied by the impedance. The impedance of a conductor depends on its length, cross-sectional area, and material. Longer conductors with smaller cross-sectional areas, and conductors made of materials with higher resistivity have higher impedance and therefore higher voltage drop. Several factors can affect voltage drop in an electrical system. These include the load current, the conductor size, the conductor length, the conductor material, and the power factor. Higher load currents, smaller conductor sizes, longer conductor lengths, conductors made of materials with higher resistivity, and lower power factors all contribute to increased voltage drop. To minimize voltage drop, it is important to use appropriately sized conductors, minimize conductor lengths, use conductors made of materials with low resistivity, and improve the power factor. Voltage drop calculations are typically performed using software tools or hand calculations based on Ohm's law and conductor impedance tables. These calculations help engineers to select appropriate conductor sizes and to design electrical systems that meet voltage drop requirements. Voltage drop limits are typically specified in electrical codes and standards, such as the National Electrical Code. These limits are designed to ensure that equipment operates properly and that the system is safe and efficient. Voltage drop can have a significant impact on the performance and efficiency of electrical systems. By carefully considering voltage drop in the design process, it is possible to minimize its effects and ensure reliable and efficient operation. Let's now talk about the National Electric Code and how it relates to voltage drop. The National Electrical Code, or NEC, is a widely adopted standard for the safe installation of electrical wiring and equipment in the United States. It is published by the National Fire Protection Association, or NFPA, and is updated every 3 years. The NEC contains specific requirements for voltage drop in electrical circuits. These requirements are designed to ensure that equipment operates properly and that the system is safe and efficient. NEC Article 210.19a provides guidelines for branch circuit conductor sizing, including considerations for voltage drop. It recommends that the voltage drop on branch circuits should not exceed 3% of the furthest outlet for power, heating, and lighting loads or combinations of these loads. Furthermore, a total voltage drop on both the feeder and branch circuit to the furthest outlet should not exceed 5%. NEC Article 215.2a provides guidelines for feeder conductor sizing, including considerations for voltage drop. It recommends that the voltage drop on feeder conductors should not exceed 3%. The NEC also provides guidelines for voltage drop calculations. These calculations are typically based on Ohm's law and conductor impedance tables. The NEC requires that voltage drop calculations be performed for all circuits to ensure that the voltage drop limits are met. The NEC provides tables of conductor properties, including impedance values, which can be used for voltage drop calculations. These tables are based on standard conductor sizes and materials. The NEC also provides examples of voltage drop calculations to illustrate the application of the code requirements. The NEC voltage drop requirements are intended to ensure that equipment operates properly and that the system is safe and efficient. By following the NEC voltage drop requirements, it is possible to minimize the effects of voltage drop and ensure reliable and efficient operation. The NEC is a comprehensive standard that covers a wide range of electrical safety topics. It is essential for electrical engineers and contractors to be familiar with the NEC requirements to ensure safe and compliant electrical installations.